Last class of 126, Malware Analysis, and all I'm planning to do is to show you Rust. Rust is the language which, for several years, developers' surveys have shown that something like 90% of developers would rather code in Rust than whatever they're coding in. It is much nicer, it is much friendlier, it is much easier to use. And in particular, the main significance here is it does not create the security problems that C and its derivatives, C++ and C# and all that have. C is responsible for almost all the serious security flaws we have, more than half of all of them, because of memory corruption caused by the fact that C does not create things like strings in a reasonable way. It creates some object called a string, which is in fact a byte array. And the fact that it's not really a string confuses developers who do quite reasonable things you might do with a string, like add two strings together and make one string longer, and then don't understand how that destroys everything. And arguably, it's not really the developer's fault. It's the language author's fault for making a language that is so hard to understand that it is very easy to make awful mistakes. And the whole point of Rust is it does not let you make those awful mistakes. If you do stupid things, dangerous things in Rust, it will just crash and put up an error message and tell you how to fix it. It is very difficult to get to shipping insecure code with Rust, and that's what I want to show you. So let's just go through a few of these. I'm going to need a Linux machine. Now I should have an ARM-based Linux machine here, which should be fine. Here's Debian 12, which should be fine. Any version of Linux really would be fine. Let's do IPA, and all right, and it's 192.168, 121, 139. So let me get an SSH in so I can use copy and paste, which is what everybody should be using anyway to get used to using a cloud. I recommend doing what I'm doing, using headless servers and connecting with them with SSH. It's a good thing to learn how to be good at. 168. 121, 139. All right, there we go. All right, so let me see what directories I have here. I do have a directory for 126, all right. Nothing in there, all right, I'll just work right here. So now that I'm in someplace, let me bring up the instructions for this project, which are down here in a Rust category. All right, so we're going to install Rust. With sudo apt update, you always do an update before you do an install because that updates the repositories. It does not update the software in the machine. You could argue this is a pretty poorly named command. It updates your list of available software, and it's really important to do that before you install things because if you don't and you have an old list, you might try to install the old version of something which is usually not available. So it's sort of baffling. You try to install something that won't go on. Now we're going to put in curl, build essential, and GDB. Curl is just a command line browser. Build essential means you have the necessary tools to build software, which are not included in default installs of Debian. And GDB is the debugger. They're all in there, probably because I've installed them before. And here's the compiler, the Rust compiler, Rust C. So now we're going to get Rust C. Now, Rust being a modern language, I think there is some way to compile single file apps in Rust, but the tutorial I followed to learn it trains you to do modern programming where you expect to make a program that will include many modules. So every program should have its own directory, which in principle would be full of all kinds of source code and subdirectories. In our case, there's only going to be one file. So this directory structure is sort of overkill, but anyway, I'm just following it. So I'm going to make a hello world app. So make a directory for it, go in there, and then I put in the source code, which is hello.rs. RS being the extension I'm going to use for Rust. It's arbitrary, of course. This is Linux, where extensions are not required. But so here's what hello world looks like in Rust. Everything's a function. It's fn, function main, just like it would be in C, except they wouldn't have the fn. Then curly braces to delimit it, and semicolons after each line, just like you have in C. White space doesn't matter. And then we print. Print line, bang, Rust says hello. So it looks not very different than what you might write in C. And so you compile it with Rust C, the Rust compiler, and then you run it with /hello. And it says, Rust says hello. Okay, so that means my compiler is working, my language is working, and so on. So let's make an integer app to show one of the simplest flaws, which is integer overflow. So here, when you define variables in C, you have to say if it's an integer or character or whatever. When you define them in Rust, you have to give more information about them. You can have an integer, you can let I equals 1, then it'll make it an integer, but it's much better to specifically specify what you want. So I is going to be an integer of some kind of default type. J is going to be an unsigned 32-bit integer. And I assign it to a value 1 and minus 5, and then I print them out. Now if I compile this one with Rust C, I get an error because I made an unsigned integer and I tried to set it to minus 5. And Rust won't let you do that. Now C will let you do something very much like that, and that's part of why you will go out of your mind, because you put numbers in variables and weird other numbers end up in them, and they expect you to know that. Rust does not expect you to know that. If you say unsigned, it says, well, what's this minus sign garbage? Which is much friendlier to the programmer. So let's try adding numbers, and this is where you get to see the first serious flaw. So I make a directory called add app, and I put in here add, here's another one. Well, if we're not going to see the first serious problem here, we're going to see another simple problem. That's right, Rust C add. I couldn't X my Rust C. All right, so there's, now again, you can't let A equals 1 because A is immutable. Consider making it mutable. By default, your variables are constants that cannot be changed. You have to make them mutable if you want them to change. So that's interesting. That might be considered an irritation and not obviously of security consequences, but anyway, that is another fact about Rust. So let's do one in C. We're going to make a C program to show off a C error. So we include a library, we got a main function, and what this is going to do is it's going to start at 230 in a character variable. Right now, this is garbage. I have a character variable and I put an integer into it. Unfortunately, this works in C, but logically, even if it was going to take integers, it shouldn't take integers over 127, because by default, integers are ASCII characters and they're only valid up to 127. So right here, something stupid is going on. And boy, it was real hard for me to learn Python 3 because I had gotten so used to this, I thought this was the way it should be. A character should be an integer that can hold any number from 0 to 255, which is stupid and wrong, but that's what we all did until modern languages like Python and Rust were written. But anyway, you start at 230, and then you're just going to add some numbers to it and print it as it gets bigger and bigger in a loop. So let's run this one, GCC, output in OVC for overflow, and now we run it. And so it starts at 231, it gets bigger and bigger and bigger, and then it gets small as it rolls over past 255, just turning into 2. This is the kind of thing that makes developers cry. You have a number, you add a number to it, now it gets smaller. How are you supposed to know that would happen? This leads to a whole ton of problems, like you have some limit on how long something should be. It shouldn't be longer than 20 characters, and it turns out that if I make it 4 billion plus 40, it's a negative number, and therefore I can put a huge amount in, even though the developer attempted to put in a limit on length. Because of this weird use of memory, it doesn't work. And this does not happen in Rust. If we do the same thing in Rust, we're going to write the same program. I make a mutable variable, unsigned 8, which is what a character is in C, and I put in 230. Now this, by the way, is not stupid. It's not a character variable. It's an unsigned single byte integer, so it's perfectly well allowed to have 230. Then I add some numbers to it and see what happens. So if I do Rust C, this one, keep hitting extra S somehow. All right, and then I run this one. Okay, it adds up, and as soon as it tries to go over 255, it has an error message. It panicked, you attempted to overflow, so you can't make this mistake. If you do, store something in a single byte and keep adding numbers until it overflows and would become 0 again, Rust stops and says that's wrong and lets you know, so you fix it. You don't go to development and ship products with this kind of bug in it. This is why developers love it. Developers would rather hear about the error than find out a year after they ship it that their product has a security vulnerability. So now we try the string overflow, the most famous one that we've all heard about, the buffer overflow. So here's a program with the simplest case of buffer overflows, where we're going to have two strings, AAA and BBBB, and we're going to input the data from the user here without limiting the length. And if we put in too much in one of these strings, it's going to leak into the second string. This is the simplest case of a string overflow where you leak from one variable into another variable. All right, so we run this one. All right. Now, I get the addresses of these. So string 1 is here at FD8, and string 2 is at FD0. So one of them is stored at FD0, and it's a series of bytes. The other one is at FD8. So if I put in string 2 longer, so I'm going to see, program asks for a new value, I put in 8 C's. Okay, so if I put in 8 characters in string 2, that's going to fill up all 8 spaces to get to where string 1 starts. And another evil thing about strings in C is they have to have a null byte at the end to terminate them. So if I put in 1, 2, 3, 4, 5, 6, 7, 8, now string 1 contains nothing, string 2 contains CCCC. So it did take the right value for string 2, but string 1 used to contain AAA, and the null byte at the end of string 2 killed string 1. So think about the poor developer. I input a string, and some other string changes, not the one I input. And of course, if you put in more, like 1, 2, 3, 4, 5, 6, 7, 8, 9 characters, now string 1 will contain 1 D, string 2 will contain 9 Ds, and so string 1 has changed from AAAA to 1D. String 2 is longer than it should be possibly. This is maddening. No wonder you get out of control and your programs drive developers nuts for doing this kind of garbage. You're supposed to somehow understand all this and keep it in your mind while you're writing code and fixing all the other problems, which is cruel. So let's do the same thing in Rust. Here's the function that does the same thing in Rust. It defines 2 mutable strings, AAA and BBBB, and then it inputs data as needed to change the second string, and then it prints them out again, just like the previous program. So we're going to use -G, so we have debugging information for this one. And then run this. It has a warning saying variable does not need to be mutable. Well, that's right, because it never changes. That would be nice. We didn't want it to change in C either, but it did change, even when we put data in the other one. Now we run it. Okay, and now we put in 8 C characters. 1, 2, 3, 4, 5, 6, 7, 8. Now notice, one string is at 70, and the other string is at 88, so they're further apart. When I put in 8, it adds those 8 to the existing A in there, so AAA, CCC, and the other string doesn't change. So, and by the way, I made it so we're inputting string 1 because we are inputting to the string before the other one. So it looks to me like if I put in 18 characters, this will overflow and hit the other string. 18 being a hexadecimal number, that's 16 plus 8, which is 24. So let's try that. If I put in 24, that's going to be 1, 2, 3, 4, 5, 6. There's 24. Let's put in some more just for fun. And what happens is it just puts it in there. It does not change the other string, BBBB, and it does not change the addresses either, A0 and B8. So that seems kind of strange. How can it not change either of the addresses and not have those strings collide? And you can see why by using GDB. So if you use GDB -Q to avoid an ugly banner, string. All right, now I'm in. Now I can list. Because I included source code debugging information, I can do source code debugging here. I don't need to go into assembly code. That's the full source code. So I can break at line 7. Line 7 is going to be after I load up the strings and print out some stuff. I'm ready to enter a new value. So before I enter a new value, I'm going to break. So let's run to there. Okay. And so it shows me AA and BBB, and here's the address FD0 and FE8. So they're 18 apart in hexadecimal, just like before. Now we can examine memory where they're stored. So I can examine 2 words of hexadecimal at the address of the first one, which is here. All right. And so there you see an address starting with zeros and then a lot of A's. It's a 64-bit address, so it takes 2 bytes. This is the high order byte first, so this is zeros followed by a bunch of A's, followed by an address. And if I do the other one, which was FE8, it's also got an address very similar, a lot of A's ending up here. Pointing, so these are pointers. The strings are not literally stored. It's 2 layers of indirection. The string variable points to an area of memory. That's another pointer that points to where the strings are really stored. And so these are 20 apart in hexadecimal. Now, I can print the actual variables. It tells me everything about S1, and you can see it's a pointer pointing to here, 1BA0, which you see up there. And I can print S2, and it's a pointer pointing to 1BC0. So this is how Rust does it. There are pointers. Now, we can see the stored strings. They're going to be in these locations. So I can do x/4x at the area that points to. And there you see the AAAA, 41, 41, 41, 41, and some zeros after it. And the next one, in my case, is at C0. So there's the B's, 42, 42, 42, 42. That's where the strings are actually stored. Now, let's add some characters. Let's add another breakpoint. I'm going to do a list. Line 10 is after it reads in the data. So let's put a break there and continue and put in 8 C's. Okay, and now we can see what it did to store them. If we print S1, S1 is still at BA0, and S2 is still at BC0. So we're still seeing the same thing as before. Both strings are still stored in the same location, but that's because there's enough room to store them both. So I can examine those memory locations. Here's one of them. There's the A's, there's the C's. It's still fitting in there, and there's even the carriage return I typed at the end to terminate it. Here's the other one. There's the B's unchanged. So that's fine. Now we're going to add 30 characters to it. So we're going to run from the beginning. Yes, to run it from the beginning. We're going to continue past the first breakpoint. And now I'm going to put in 30 characters. 5, 6, 7, 8, 9, 10. Which is enough that it will not fit in the gap between these two added to them. And now, when you print S1 and print S2, you're going to see what it did. S1 now points to a completely different address, BF0. S2 still points to BC0. This used to be BA0, so what it did was it went and allocated new memory someplace that's big enough to hold the string, which is just what a sensible developer would say. If I make the string bigger, then obviously what I want you to do is to find some place in memory to store a bigger string and store it correctly. I don't want you running on top of some other variable and destroying my life. So that's how it works. It's pretty cool. So it's pretty logical. Anyway, let me get out of here. And so, by the way, command injection is where you put a command on the same line as another command and execute it when you have this system command. If you actually do call the OS system on a string that came from the user, then you have a command injection vulnerability. This is the thing that does the ping minus C1 of the data. And you can do that in Rust. That is not a defect of the language. You can do it in Rust. If you're going to do that in Rust, it's a little harder to do, but you can run in command, ping C, taking data from the user, the IP. And if you're dumb enough to write a program like that, it is still going to have a command injection vulnerability in Rust, obviously. That's the thing. That is the kind of logical flaw which you can't prevent. All right. And that's all I wanted to show you about the first one. I've got another one to show you, R20, but I want to take a 10-minute break first. I'll be back at 6:40. I'm going to stop this recording.